Okay, let's dive right into this explainer where we're going to unlock some seriously powerful algebra cheat codes for polynomial special products. I mean, if you've ever felt like multiplying polynomials takes just way too long, you are absolutely in the right place. We're going to reveal the hidden architecture inside these expressions that'll save you time and honestly, dramatically reduce your errors. So here's our roadmap for today. We're hitting the most common math mistake, unlocking perfect squares, the difference of squares, verify your work, and finally, recap and transfer. Starting right off with part 1, the most common math mistake. You know, it is incredibly tempting to see a plus b all squared and just kind of distribute that little exponent to get a squared plus b squared. But actually, scratch that. Think about the area of a square. Squaring a binomial is literally never as simple as just squaring the first and last pieces. There is a whole middle section you're missing. The true expansion is a squared plus 2ab plus b squared. Which brings us to part 2, unlocking perfect squares. So when we say a plus b squared, what we actually mean is the quantity a plus b multiplied by itself. By using standard distribution, good old FOIL, we multiply the first terms to get a squared. Then, the outside terms give us AB, the inside terms give us BA, which, let's be real, is the exact same as AB. And finally, the last terms give us B squared. When we combine those two identical middle terms, they stack together to create that absolutely essential middle piece, plus 2AB. And this brilliantly illustrates what happens when we swap that addition out for subtraction. The pattern is basically identical. When we distribute a minus b times a minus b, well, a negative times a positive gives us a negative AB. We get two of those. Then a negative b times a negative b gives us a positive b squared at the tail end. So the only difference in our final polynomial is that our middle term sign flips to negative, giving us minus 2ab. Now, the absolute most critical takeaway here is that this middle term, it's the true VIP of the equation. Whether it's plus 2ab or minus 2ab, it carries the sign that defines the entire polynomial. It completely bridges the gap between those squared ends. So basically, whenever you square a binomial, your brain should immediately start looking for this middle term. Okay, let's test this out in practice. Check out this expression. If we have the quantity x minus 5 all squared, what's that middle term going to be? Let's break it down together. If you identified the pieces, your a is x and your b is 5. Following our pattern for subtraction, the middle term is negative 2 times a times b. So that's negative 2 times x times 5, which gives us negative 10x, making our final polynomial x squared minus 10x plus 25. If you nailed that negative 10x in the middle, awesome job. You just successfully avoided the most common mistake in algebra. Moving on to part 3, the difference of squares. Now for a pattern that honestly feels a bit like a magic trick. What happens if we mix the signs up? Like, what if we multiply a sum, a plus b, by a difference, a minus b? Well, let's distribute it out. We get a squared minus ab plus ab minus b squared. Look really closely at the middle there. A negative ab and a positive ab, they literally destroy each other. They cancel out entirely. And that leaves us with a middle term of absolute 0. Because those inner and outer products are exact opposites, they completely vanish, which proves exactly why a plus b times a minus b simplifies so beautifully to just a squared minus b squared. It's super clean. This is what we call the difference of squares. Let's do another quick check for understanding here. We've got the quantity 2x plus 3 times the quantity 2x minus 3. How does our 0 middle term rule apply to this one? Well, because we can instantly recognize that plus and minus pattern of the exact same terms, we know for a fact the middle term just disappears into 0. We don't even have to write the whole thing out. We just square the first term, 2x, which gives us 4x squared. Then we square the second term, 3, to get 9, and just stick a subtraction sign right in the middle. It simplifies effortlessly to 4x squared minus 9. All right, part 4, verify your work. Now, shortcuts are fantastic, but when you're first using these patterns, it's incredibly helpful to verify them so you know you're on solid ground. Let's take x plus 4 squared. Using our special product rule, we know it's the first term squared plus 2 times both terms plus the last term squared. That gives us x squared plus 8x plus 16. Now, let's verify that with ordinary binomial multiplication, x plus 4 times x plus 4. Distribute that out to get x squared plus 4x plus 4x plus 16. combine those middle terms, and yep, we get x squared plus 8x plus 16. By verifying our shortcut against regular old distribution, we confirm they yield the exact same polynomial. It proves these special product rules are built on a rock-solid mathematical foundation.
And finally, Part 5, Recap and Transfer.
Viewing these three identities side by side like this really anchors your attention exactly where it needs to be, on the shifting behavior of that crucial middle term. For a sum squared, it's positive 2ab. For a difference squared, it's negative 2ab. And for the difference of squares, the middle term is just 0. I'm telling you, memorizing this right here will save you countless hours down the road. But why does this all matter? The educational standards remind us that algebra isn't just about shuffling random letters around a page. It's about seeing the underlying architecture of mathematics. When you can look at a seemingly complicated expression and recognize it as a single structural object, like a perfect square, you're elevating your math proficiency to a whole new level. And get this, you can actually transfer this algebraic structure to real, everyday life. Want to find the square of 31 in your head? Easy. Just treat it as a polynomial special product. 31 is really just 30 plus 1, right? So 30 plus 1 all squared. Apply our pattern. 30 squared is 900. 2 times 30 times 1 is 60. 1 squared is 1. 900 plus 60 plus 1 is 961. Boom! You just used algebra to perform mental math magic. That is the true power of understanding structure. So, if you can use algebraic patterns to solve complex arithmetic entirely in your head, what other hidden structures are waiting to be uncovered in your next math problem? Keep looking for those patterns, and until next time, keep exploring the structures all around you.